All right, we're going to take a look at the second half of the mechanical advantages, counting tensions, and estimating system efficiencies. We took a look at the counting tensions part on our last one. This time we're going to actually add friction into it and see what happens. So when counting tensions determined the theoretical mechanical advantage, it was theoretical because we ignored friction. We're now going to estimate what the mechanical advantage is in various systems when friction is appreciated just within the pulleys. As far as a couple discussion points, when discussing counting tensions, we assume no friction. So one tension entered a pulley and one tension would exit. What this means to the rescuer is that the mechanical advantage you believe you've created is actually not that mechanical advantage. So we never actually get to a 2-to-1, a 3-to-1, a 4-to-1. Those are all theoretical. What we are going to do is add the friction in of just what's in the pulleys and kind of see what comes out. And when we use various equipment, how that kind of changes the entire system. Every pulley in our system contains some friction to various degrees. This is based on multiple variables, like mainly what the pulley construction is. Is it a bushing pulley versus a sealed bearings, along with other factors that we'll actually discuss a little bit later in this presentation. We'll review a few common devices and what their efficiencies are and what it means to your mechanical advantage system. Remember, we're still not taking into account any of the friction that we gain over edges or other system contact areas. That's going to be for another video cast in the future. All right, so what we're looking at is we're estimating the following efficiency values. These are derived from a 1-to-1 pull of a 185-pound load. If we made it 200 pounds, we're going to get something a little bit different. The rope we use was a fairly new 7.5 millimeter aramid sheath rope, also an aramid core on that also with a 32 carrier. When we looked at these, we pulled them on a 1-to-1, and we'll kind of talk about how that 1-to-1 number that we get may change a little bit depending on where it is in the system a little bit later. So when we looked at the Rock Exotica mini machine pulley, we had an efficiency of right around 90%. The aluminum 7075 oval carabiner is roughly 45%. The Gree 2 efficiency was right around 28%. We also looked at the EXO, which was a little bit less than the Gree 2. The other side that we need to kind of keep in mind when we're looking at this too is we were using a 7.5 millimeter rope when we were doing this. So the coefficient of friction, the diameter, everything may change a little bit. So if you see numbers where people are like, hey, we usually count our carabiners at 50%. And that may be accurate for the carabiner that you're using, depending on the material of the carabiner, the material of the rope, and the construction of the rope. So this is what we had with this, just to kind of give an example. All right, first we're going to look at how those efficiencies are, and then we're going to take a look at what that means as far as pounds and percentages and things like this. So when we look at this, we're using high efficiency pulleys in the system right here. So this is obviously set up as a 3-to-1. When we looked at it before, we always remembered, oh, we have one tension that comes in and we have one tension that comes out. In this case, we have 90% efficiency pulleys, which means that if one tension goes in, 0.9 comes out. As 0.9 travels up, 0.81 comes out. Just as before, when it was 1 on 1, that would equal 2 here. Now it is 1 plus 0.9, which gives us 1.9 on this prusik. As that 9 comes up, 0.81 comes out. We have 1.71 here on the anchor point. 0.81 travels down. 0.81, because we have a rope grab, is added to what's the rope grab is holding, which is 1.9, and that gives us a 2.71 to 1 mechanical advantage. So when we think about this, a lot of times we'll hear from various groups of, hey, I'm just going to use my EXO bailout system and use that as my 3-to-1. Or we'll use this ATC as our progressive capture or whatever. And that's probably really good to know in case you have nothing else. But just so you realize, even though we look at this one on the right and it looks like a 3-to-1, and without understanding the friction we're talking about, we've literally had people believe that this was just as efficient as a system that had a micro traction and high efficiency pulleys on it. So what you may hear is, hey, I'm going super fast and light, and I'm going to use this Grigri 2 or this EXO, and I'm not going to bother with the pulley. I'm just going to gain a little bit of friction on that carabiner. So we see kind of the effects of that now, as if we have one come in, as we talked about before, the carabiner is going to roughly be 45% efficient for us. One comes in, 0.45 comes out, which means we're holding 1.45 on this prusik here, or the rope grab, T-block, whatever you're using. The 0.45 comes up, and because we're dealing with a 28% efficiency in this Grigri 2, we have 0.126 come out. That 0.126 that comes out meets with our 1.45, and we have a total of a 1.576, or roughly approximately a 1.6 to 1 mechanical advantage that we believed we had a 3 to 1. So with the above graphic here, we can see the effect of pulley friction. We already said we'll probably have other frictions affecting us in real-world applications like the edge. But we also have friction within these prusiks that we're not even mentioning in here. We're just assuming this was not adding any friction to it. But in real life, what you're going to find is those prusiks that we're using, whether it's a single or a tandem prusik, at our progressive capture is actually going to add friction also. Unless we're using something like a micro traction, a JAG, or something like an MPD, then we wouldn't have that issue. But realize that when you're doing this and you're trying to test that efficiency, if you do use a prusik minding pulley or prusik system as your progressive capture, then you're going to want to see what that friction is when we look at that. Another question that typically comes up here is when we talk about everything being equal and what comes in has to come out, people ask what happened to this 10%. So that law kind of goes out the window apparently, and it actually really doesn't. So what happened to the 10% loss is energy was actually transformed. So in this case, the friction transformed to heat, and that heat basically dispersed into the atmosphere. The balance is given off in heat. Just remember, the lower efficiency of your device, the more heat that's actually gonna produce. So if you think about your descent devices, and whether you're on an AID or an ATC and you go basically rappelling, and that device is made to keep your body from going 9.8 meters per second squared to the ground. So it's going to produce some heat. You probably felt that heat when you got to the bottom, and even a munter or a 3 wrap on your spine, you're going to have quite a bit of heat generated in there, because that is the friction that's keeping your body hitting and splatting onto the ground. So oddly enough, we actually see people teaching and companies selling kits that say that their system creates a 3 to 1, a 5 to 1, or whatever MA system that they're talking about, yet they use descent devices or belay devices as their progressive captures in those systems, which is really kind of the opposite of what you want, right? In Hall systems, we want to decrease the friction every chance we get, and lowering it's awesome. So as a belay system, as a the lowering device or descent device, that's incredible, that friction. But thinking that we're going to be able to turn around and use that device in a progressive capture and having anything even remotely close to efficient is just really wrong. There's no way you can actually screw with physics enough to have that happen. So think about your mission. Think about how you roll in your team. If you're a group that is organically depleted as far as assets go, and you're low personnel, fast moving, you're probably going to want something more efficient. If you're rolling with a bunch of people on a USAR team, and you got a bunch of guys, 15 guys ready to haul on that rope, then high efficiency gear probably doesn't take a priority with you. So what we're going to do is look here in a couple slides. We're going to show you what that weight looks like, and we're also going to show you kind of some percentages. So when we look at this, it's exactly what we looked at before. This time we're basically going to look at what that means as far as poundage or weight that we're inputting into that system to come out. So in the end, we're just going to assume that the load is 200 pounds. So to figure that out, now that we know somewhat closer to what our actual mechanical advantages, we can take 200 and then we can just divide that out by 2.71. When we do that, we get 73.80 pounds. So 73.80 pounds is what we're going to have to input as haulers into that system. But what we can see is what happens to that 73.80 pounds as it goes through our system. So right off the bat, we input our 73.80, which after our loss of just 10% because this is 90% efficient pulley, we get 66.42 pounds, which leaves us with 140 pounds sitting here on our pulley. That 66.42 comes up, and after we go through another high efficiency progressive capture, 59.78 comes out, and we're left with about 126.2 pounds on our anchor. As that 59.78 comes down, it meets up and is added to our 140, which gives us our 200 pounds. So everything equals out there, and that's how our 200 pounds is dispersed through that system as far as what's lost. Where things start getting slightly depressing is when we go over to the right-hand side, where we lose a bunch to friction. So we can see that with our 1.61, or we actually take it by 1.576 and divide that 200 by 1.576, we get 126.90 as far as our input pounds that we're going to have to put in there. So as we input that 126.90 pounds, after it goes through this carabiner, we're only left with 57.105, which means we have 184.005 sitting on this carabiner and this rope grab. Now we know that we're going to lose a butt ton to friction in this device here. So as 57.105 comes in, we are actually left with roughly 16 pounds, 15.99 pounds coming out that other end. That 15 matches up with our 184, and we get 199.995, or roughly 200 pounds. So that is how that is dispersed through that system, and we can see how that large input of what we're putting in, what actually comes out of it, begins to get pretty depressing. All right, same thing on this one. Another way we can look at these numbers is as a percentage. So a percentage of your input force. So if we look at the diagram here on the left and we put 100% of your input force in, which would be that one. So whether you put 70 pounds or you pull as much as your pinky can pull or whatever that is, you have 15 people pulling on that. Whatever that poundage is, it's 100% of what you input. So as that 100% comes in, and we're dealing with a very high friction, low efficiency carabiner here, as that one comes in, 0.45, so 45% comes out. So out of that 100, 45% comes out, which means this is holding 145% of your input. As 45% comes in, roughly 12 to 13% comes out that other side. As that comes down, it meets in with our 145%, and we get a total of 157%, roughly 160%. So in reality, we're looking at a 3-to-1, which it would be awesome the closer we could get to 300%, right? Because it's 300%, so it's 3-to-1, so 100 in, 300 out. We're only left with approximately 160% of that. What's interesting, though, is if we're going fast and light, and we're like, this sucks, man, I can't move this. You know what we can do? Let's just slap a rope grab on here, do a change of direction with a carabiner, and now we'll have a 5-to-1 complex. Well, what gets interesting here when we talk about friction is you eventually are going to reach a tipping point where you will just start losing your mechanical advantage. So interestingly enough, when we look at the right here and we convert that to a 5-to-1, we actually have hit that tipping point where the friction is just insurmountable, if you will, and we actually lose every bit of MA. So this 5-to-1 system actually has a lesser MA than this 3-to-1. We actually drop all the way down to basically a 1.1-to-1 when we build this, because each one we're losing so much to friction that we actually lose it and we are now screwed. So thinking that we can move fast and light, we can if we use the right gear. Doing it this way is probably nothing that I would suggest that we do. So now a 5-to-1 is not a 5-to-1. We're going to look at a couple of 5-to-1 systems that we have here. The one on the far left is what we commonly see. A lot of firefighters, fire departments use that USAR teams where it's just a 5-to-1, simple 5-to-1. This is, we split these carabiners up here. This is usually a double pulley, but we split them up so we can kind of count it easy. And we'll see everything in this is high efficiency. So looking at best case scenario, not even worried about what's going over the edge or anything like that, that 5-to-1 simple actually rolls out to be basically a 4.095 or roughly a 4.1-to-1. When we look over to the complex system that we talked about before, we actually get a little bit better on this one. All still high efficiency, but we come out at a 4.149. or a 4.2 to 1 roughly. Why is this? Because we know that every carabiner or every pulley gives us friction, and if you count the amount of pulleys in this one, we have 4. Even though this is 1, it's got 2 sheaves, so that counts as 2. So we've got 4. By just decreasing a pulley out of our system, we're able to gain more of a mechanical advantage. Oddly enough, when we look at the Spanish Burton over here, we actually see a pretty darn efficient one, that most efficient. Unfortunately, it's just going to take more equipment and pretty unrealistic to build in most cases unless we're mountaineering or something like that. So why does it get that? Is because on this one it's a single rope going through all these that just gradually loses more in that one system. On this one it actually terminates, and we have a second system that starts to bear it, so it actually retains more of its mechanical advantage on that one. So same kit, where does the pulley go? If we find ourselves limited as far as our kit goes and we have a progressive capture, whether that is a pulley with a Prusik or it's a micro traction, so we can say, just for argument's sake, let's say we have a micro traction and we have 1 pulley. So where does that pulley go? So we can go through and see that the most advantageous area for us to do is going to be right here, which means that I want to put my most efficient pulley as close to where my hands are hauling on that rope as possible. So this is even the case, let's say if I had a sealed bearing pulley right here, which is going to be roughly about 90%, compared to a bushing, an older bushing pulley that's somewhere probably in the 72 range. If that was the case, I would still want my 90% here, and I could put that 72% further away in my mechanical advantage. So by keeping and preserving as much of your input force right off the bat is going to increase that mechanical advantage. So we have the same equipment across the boards here, but when we look at this, this is obviously the most advantageous. So the one last thing I want to hit on too is when we're looking at some of the things like a gree or anything like that, realize that I can have a terrible efficiency right here, but if I had really high efficiency or better efficiency things throughout that system and pulled on it, it would actually make this, as my mechanical advantage kind of goes up from a 3 to 1, let's say, to a 5 to 1, that efficiency that I got on a 1 to 1 rating for that device would actually become a little bit better because I'm taking some of that load off of it. Yet it's still, realize, made to produce a lot of friction. And that is the end of part 2 of mechanical advantages, counting tensions, and estimating system efficiency.